basically just starting in engineering, and yeah, I'm going to tell you about my research, which is in modeling materials using machine learning methods. So first of all, what is a material? Well, materials are the building blocks of our world, from the concrete and steel that hold up this building, to the fabric that makes for the clothes that we wear, to the silicon and the electronic components that are showing this image, once it comes up, that are showing this image. To even including, the skin, bones, and muscles that hold our bodies together and allow us to move. And with advances in materials like this, we can do some pretty amazing things. We can build buildings that reach almost a kilometer off the ground. We can make clothes that repel water, fire, or even bullets. We can make computers that are very powerful, small, and fit in our pockets. And sometime in the future, we may be able to even custom make tissues and organs to replace parts of us that have stopped working. But if we want to keep on making these advances, we want to keep on doing great things with materials, we need to keep developing our understanding of how they work, why a material is so good at its job, and what goes on inside of it to make it do that. And that is the sort of science that I do. I model materials. I use computational and theoretical methods to compute the properties of materials at the atomistic level. So if there are any experimentalists in the audience, you may be thinking, well, why do we need to do simulations? I mean, we can just make a material and characterize it. We can do experiments to figure out what it does. Well, there are a few reasons that simulations have been used for decades at the very least to go alongside experiments to help us figure out how materials work. And one of them is that, well, not only are simulations very predictive, they have lots of predictive power, but they're also much cheaper than doing an experiment. Like in the time that it takes you to fabricate a material, to run it through a battery of tests, you could have done simulations on thousands of different variations on that material. So really, simulation goes alongside experiment, works alongside experiment. Experimentalists, may uncover things that we haven't seen before, that point out deficiencies in our model that we need to change. While our simulations tell the experimentalists, where's the best place to spend their time and where they shouldn't waste any of their time, right? So yeah, I'll take you through the sort of things that I do to predict the properties of materials and what I'm doing to improve the models that we already have. So I said that I do materials modeling at the atomistic scale. That means we take into account every single atom, every single molecule that makes up a material. Now, it's easy to just talk about atoms and molecules, but I want to give you an idea of how small that really is. How small is the atomistic scale? So let's start. I will use this XNX KCD comic as visual aid. So let's start at our everyday human scale. Things that we can see, that we can pick up and move. This room, for comparison, is about 5 meters wide. The things that we interact with, like desks and chairs and whatnot, are maybe 1 meter to about a centimeter wide, pencils, that sort of thing. The smallest thing that we interact with generally every day is about 1 millimeter wide. That's about the width of a grain of rice. So if we take that millimeter and zoom in on it, we zoom in on the grain of rice, expand it until it's the width of this room, we can start seeing a lot more detail. We can start seeing human cells, like human hair is maybe about this wide. And if we look closer, you can even see bacteria. They're maybe about this wide, like a single E. coli might be about this wide. So let's take a closer look. Take our millimeter, again, expand it so that it's the size of this room. And we can see even more detail. So our bacterium now about fills the Churchill College dining hall. We can see like the cell membrane. We can see strands of DNA floating around. A single strand of DNA might be about this wide. And if you look really closely at that, you can start seeing that it's made out of little individual atoms and molecules. So that is the scale at which I do the simulation. So 2 big zooms of 5,000 times, and you can start to see the individual atoms and molecules. Now, in doing that, we've completely left behind the world of classical mechanics that you may have left in high school. Things no longer behave as we expect them. Everything is governed by the laws of by the really weird laws of quantum mechanics that we phrase nowadays in terms of this equation, only equation in the talk, I promise. It's the Schrodinger equation. So what it tells us, more or less, is we list in this H all the ways in which the atoms, in which the electrons and nuclei in a material can interact. Once we solve it, we get out this psi thing, which tells us basically where the electrons are located in the material at what probability. And we get an E, an energy, which tells us how favorable that configuration is, basically. Now, it's a little bit more complicated than this looks. but we can solve it. There are lots of different ways at many different levels of approximation and correspondingly at different levels of computational expense to solve this equation, and you can actually get out this probability distribution, this psi, and this energy. So now the question is, what do we do with it? I mean, why did we go down to the scale in the first place? So there are a few properties which are actually determined that by the composition of matter out of atoms and molecules. Like if you do any type of spectroscopy, infrared, X-ray, and NMR, you're basically interacting with individual atoms, with individual like bonds or nuclei in the material. You're depending on the matter to be made out of molecules. And there are other things, like what we call intrinsic properties, things like density and viscosity of a material that don't change when you take a smaller part of it, until you get down to the animistic level, because then you're taking apart individual little atoms and molecules. So we need to go down to that scale to actually figure out what's going on to give the material its density or its viscosity. Now the question is, how do we do that? I mean, once we know how to solve the Schrodinger equation, how do we turn that into some sort of simulation that will let us get this density, get this viscosity? So we can't exactly just simulate all the atoms in this glass of water, because there are about 10 to the 23rd of them in here. In order to simulate every single water molecule in this glass, we need a computer several times the size of the universe. So we can't exactly do that, but we can use a little trick. We can take a small box, maybe a few nanometers wide, pack it full of molecules in our computer, of course, and glue one side of the box to the other computationally. So we have what looks like an infinite piece of material, although we're only really simulating maybe a few thousand molecules, which is completely within the range of current computers, Earth-sized computers. So what we do then is we just let these atoms in the box evolve under Schrodinger's equation, and once we let it run long enough, we can start measuring these properties like density or viscosity if we do things to the box. And once we let it run long enough, we can start gathering statistics, because we need to get these properties with a very small uncertainty. And then we can come back to the experimentals with the prediction. This is what the Schrodinger equation tells us the density of this material is. So there's a problem, unfortunately, because solving a Schrodinger equation is really, really expensive. Even with the fastest level of with the highest level of quantum mechanical computations, with the fastest computations that we have, we need to simulate, let's see, maybe about 10,000 atoms for hundreds of thousands of configurations to get acceptable statistics on these properties that we're measuring. And in order to do that, it would take months with the fastest methods that we have available. So what we need is a faster way to approximate that energy. And people have been doing this for about a century now, trying to approximate Schrodinger's equation. They've been coming up with these things called interatomic potentials. So basically, you assign part of that energy to each atom in a molecule, and then you say that each of these atoms interacts with its neighbors in some way. Like you write down a function which you think describes how the atoms interact with each other. And then at the end you add up all the energies for the atoms to get the total quantum mechanical energy. The earliest example of such an approximation is called the LennardJones Potential. Some of you might have heard of it, but it's a very simple concept. You just take two atoms. This axis is the distance between the atoms if they're very far apart. You can think of this as a ball rolling on a hill. If they're very far apart, it's a very flat region of the surface, they don't really feel much at all. Once you start taking them closer, the surface starts sloping downwards, they start feeling an attraction, and when they get really close, they're happy. If you push them too close, however, there's this really steep wall that keeps them from getting too close. And this sort of agrees with our intuitions about how atoms in molecules are just floating around freely should interact. We just take this potential energy somewhat across all the pairs that are within some distance in our material, and we get a total energy. And we can take this approach and extend it to almost arbitrary complexity. We can make this functional form. We can make the form of this interaction more complex. We can add things like pairs, triplets. We can add so many more parameters, and that can get you more accuracy. but it's not a really systematic way of proving an approximation to this Schrodinger equation. So, and often because they're not, these approximations aren't actually designed to approximate the true quantum mechanical energy, but rather just, the parameters are tuned so that simulations reproduce what we get out of experiments. They might not be very accurate if you try new things with them. So we want transferable and systematic approximations to the underlying quantum mechanical energy, and that is what our group has been working on for the past however many years. Yeah, so the trick that allows us to do this systematically is we notice that if we're solving the Schrodinger equation for every single configuration that we're given, well, we're actually being inefficient. We're actually throwing away information, because if you change a molecule by a very little bit, you wouldn't expect this total energy E to change by all that much. So if you're computing energies for lots of similar geometries, you're wasting information. So that tells us that we can be so much more efficient with quantum mechanical data that we're given. We could just solve the equation for a sample of geometries, and then for anything new that we're given, sort of interpolate between these to get the energy that we're after, right? So yeah, if you're familiar with machine learning, this next slide will make sense to you, but machine learning really just means that we're finding a way to interpolate between the data that we already have. So if you're familiar with machine learning, what we're using is called Gaussian process regression. So what we do is we more or less consider every single potential energy surface that could be possible. So if this is hard to visualize, and I'm sure it is, just think about two atoms, just like our LennardJones example. Think about how two atoms might interact and all the possible curves that could describe, sort of the potential energy of a pair of atoms. And we take each of those curves and assign them a probability. Now, when we do a quantum mechanical computation, like the energy of this pair of atoms, that sort of constrains the possible potential energy surfaces that we could have at that point. So we just do a whole bunch of quantum mechanical computations that sort of tells us, that pinches down the probability distribution like you see in this picture. And we not only get a prediction for what the energy is at any intermediate point, we also know how certain we are in that prediction. So that's really nice feature of Gaussian process regression. But if you didn't understand that, all this means is that we're fitting a function to data in some really optimal way. Okay, so yeah, we do the same trick that we did earlier with interatomic potentials. We assign an energy to each atom, and we learn using this Gaussian process regression. We learn the atomic energy as a function of its local environment. Right. So this approach that's been developed a few years ago, it's called Gaussian approximation potentials, and it's been used for very successfully for lots of solid-state materials like iron and tungsten and that sort of thing. So I tried it, as the first part of my project. I tried it on more molecular sort of things. Like I tried it on these, which are like molecules that you might find in diesel. And what I got out is, again, that any potential, these three potentials are Gaussian approximation potentials. This is an existing potential that's been developed in some sort of other unsystematic way. We find out even with the simplest sort of descriptions of the local environments, we already start outperforming the existing potential. So yeah, that's a nice result. It shows that this approach can work for molecules where you can represent the total energy as a sum of local energies, where you can distribute the energy among all the atoms. But unfortunately, that's not always the case, because in a lot of molecules, if you take one part of a molecule or another molecule somewhere else and wiggle it, it's going to affect this local energy, this energy that you thought was local, that you were trying to learn. And the obvious question is, why don't we just use larger local environments? Why don't we just learn as a function of the molecule or the simulation box? And the problem with that is it's an issue of complexity. So if you make your local environments larger, that means there's so many more configurations that you can pack into it. It's a combinatorial explosion, which means you need so many more training examples for the machine learning method to give sensible answers. So we have to keep the local environment small in order to actually get any advantage out of this method, and have to find some other way to account for these outside influences on our local energy. Right? So that's basically my project. Like the first part of my project was to quantify, figure out how much these external influences actually affect the local energy, how much error do we get by ignoring them. and then to start finding ways to account for these outside contributions. So one of the first things that I tried was accounting for a relatively simple interaction called that we normally just call electrostatics. So this is what happens when there are atoms in your molecule, like in this case oxygen atoms, that pull lots of charge towards themselves, and they pull the charge distribution of the molecule out of balance. So there's lots of negative charge here, there's some more positive charge here. And so since the electrostatic interaction is very long range, this means that your local energy can be easily affected by something that's going on over here. So there's a way we can account for this sort of interaction. Remember the other piece of information we got out of solving the Schrodinger equation. So far I've been focusing on the energy E, but we can also get out an electron distribution, this psi thing that tells us where the electrons are located in space. And from that we can figure out how much the charge has been distorted, and we can use various ways to compute what exactly this outside force is, so we can subtract it off and be left with the local energy that we can then put into our machine learning method and learn accurately. So if this sort of work is successful, we will have a potential that works for molecular systems as well, that is based systematically on the underlying quantum mechanical description. So it's accurate and it's transferable, and it is as accurate as solving the Schrodinger equation, more or less, but with several orders of magnitude less computational expense. And with that, we'll be able to tackle much bigger, more complex materials, figure out how they work, and once we do that, hopefully start giving input in the design of new materials. Right, and so before I close, I'd like to thank my supervisor, Gaussian Chanyi, and everyone in his research group for lots of useful discussions, as well as Shell for funding my PhD, and you for listening.
Okay, so I guess now it's time for some questions. So who has some exciting questions?
I have a question. Okay, you said that you find the electron densities through the Schrodinger equation, right?
Yep. Yeah.
So, and you're trying to figure out how to expedite the process. So you would already have to have solved the Schrodinger equation and then do a feedback with that info, right?
This is the part that I missed. Right, I should have, I should have also said that the only way that we can get benefit out of this is, so we get these what are called partial charges, these things that tell us how distorted the electron density is and how much different parts of the molecule interact. We get these partial charges out, but we can learn those in the exact same way that we did for the local energy. So we're learning, we're learning the local energy, we're learning the partial charge. And so then we have one thing that accounts for the local part of the energy and this other thing that accounts for the long range part of the energy. But we still only have to solve the Schrodinger equation at a very small sample of geometries. Make sense?
Yeah.
Yes?
How do you assign the probability distribution initially for your potential energy and what you're going to learn? And how much does that affect the results?
So this is actually a central problem in what's called Bayesian statistics. So what you asked is the question of selecting a prior.
Yeah.
What do we know about the problem before you've even started? So let's go back to this example of this just learning the Leonard-Jones potential. Right? So we already know a few things about the system. We know on what energy scales these interactions take place. It's not going to be like move the atoms together, they snap together, and it's going to be like a mega electron volt of a potential well, because that would just be silly. You would have a nuclear weapon in the Leonard-Jones potential. So we think that, we know from experience that the interactions on the atomic scale, let's go back to you, take place on the energy scale of about electron volts, and we know the scale of variations. It's not like we're going to move them a tiny bit closer together and all of a sudden the energy is going to jump to something completely different. We know it's going to vary relatively smoothly, like on the order of maybe about an angstrom or so. So we put that in to our probability distribution over functions, which we can do with Gaussian processes. And then so that's the selection of prior. But once we get in enough data, that actually starts to overweigh the prior. I should have written Bayes' rule in here somewhere, but that would have been more than one equation in the talk.
Yeah, so one thing I didn't understand, so when you get the data and then you have your posterior, but isn't your data, I don't. Isn't your data coming from your simulation that depended on the prior?
No, your data is coming from directly solving the Schrodinger equation. It's coming from that doesn't necessarily depend on the prior. That's just fundamental physical laws that we know work.
Oh, okay.
Our
so
prior
your data. What's your data then?
Our data is, you can think of it as every time we solve the Schrodinger equation and get an energy out of that, that's a point of data. Or like we have a way of figuring out what's the local energy, like how do we assign the energies to each of these atoms. And once we solve the Schrodinger equation, we can do that assignment and then find out, and then our data point is like, what is this local energy for this atom in its neighborhood? That's a data point.
And then, sorry to keep asking, but then I'm assuming when you're gonna have a lot of data points. So what is the thing that varies when you get another data point? Like why would they not?
It would be like the local geometry. So you do a configuration.
Oh, okay, I see.
You do a computation at another configuration.
Okay.
You just have a sample of configurations, then you do the computations. Yeah. Yes.
Is this for like polymer applications? Is that basically what?
So the first application that we're exploring right now is, as I said, density and viscosity, but of hydrocarbon liquids. So things like, so diesel fuel is a good starting point. It's, like diesel fuel substitutes, like 7 or 8 carbon atom chains floating around in liquidy state. The reason that Gaussian approximation potentials are a good application for this, once you get this problem of long-range interaction solved, is that for liquids you just need so many more atoms in your simulation box, and you just need so many more time steps, so many more configurations of your box to get acceptable statistics on the properties that you're trying to measure.
And what was I going to ask? I'll come back to it, I guess.
All right.
Which inference method are you using for the Gaussian processes to get the posterior?
Which inference method?
Yeah.
I've always thought of Gaussian processes as an inference method. So once you drop down a data point with the sort of with the sort of error bar that you associate with it,
is it like an MCMC based one, or is it variational?
You don't need to use MCMC. The only thing that happens is matrix inversion. So you take the covariance. So what happens in the background, and there's another way of phrasing this actually. What happens in the background is basically you take the covariance, and we define the covariance function in some way, which is like a similarity between local environments. But you take the covariance of every single data point, between every single data point that you've already computed, make a matrix out of that, and then for each new data point, you take the covariance of that and every existing data point, and then you invert the matrix, multiply by that thing to get your prediction.
Does that mean that all the parameters for the covariance function, etc., are known ahead of time?
They're what are called hyperparameters.
Yeah.
Yes. So that almost goes back to the question of prior selection. So what goes into covariance function? This thing about the spatial variation, the spatial length scale of the variation of your function, that's part of your prior, but it's also a parameter that goes into the selection of the covariance function.
Mm-hmm. Okay.
Yes.
You said you had a box with periodic boundary conditions.
Yes.
With some large number of molecules in, which that large number was what, like 10,000 or something?
Yeah, it can be about 10,000, I think.
So why couldn't you do it with a box with 10 molecules in, and then the periodic boundary conditions, and then long range effects are allowed for by the periodic boundary conditions?
So a few things, like in liquids, there's structure that extends way beyond that extends beyond. If you had like a box with 10 molecules in it, it's a tiny, tiny box. And so what you've basically got is a copy of this box, like infinitely repeated. There's no way you can sample all the sorts of different configurations that actually happen in an infinite liquid with just the 10 atoms or 10 molecules or whatever in this box. Because you're going to see the same pattern just repeated over and over again. There's structure in liquids that you need huge supercells to capture.
But you were repeating the simulation anyway, right?
Yeah, but there are different. But you can repeat at different scales. Like I can say, oh, my box is like this big, and I'm going to fill it with 1,000 atoms, and I'm going to repeat that. So you have repetitions at a much larger scale, and you hope you can capture a lot more complex structure that way. Yes?
So when you're talking about long-range interactions, do you mean long-range interactions of orders of between several molecules or between several atoms in a single molecule?
It can be both. So like with this electrostatics example, it very often is both, because, well, yeah, I mean, there can be polarization. It gets a little bit hard to define this line when when the molecules are big and floppy and different parts, then like each end is essentially independent of the other, right? Like with proteins, that sort of starts to happen when you have different ends that are not really. It's a bit more like moving a chain than moving a rod, right? Yeah.
So do you ever do any simulations on like stiffer molecules, which they're not electrostatic interactions, but obviously one end will still affect the other quite a lot.
Three-fold.
Yeah, those are what we might call pathological cases. So one of those is I think they call it polyacetylene. That's like where there's double bonds all the way along the chain, and so that's something that we normally not see in a diesel molecule, in a diesel fuel that we hope. But there are problems, like you change something at one end, and some weird thing happens with the electrons at the other end. Yeah, I think that what I described was called charge transfer excitation, and they are the bane of the DFT community.
By conjugated bonds.
I think so. Yeah, there's certain there are certain types of molecules where you change one end, and or maybe there's an excitation which, how does that work? Well, yeah, so there are lots of different ways that you can have like rigid molecules, stuff changes at one end that affects the other that we can't quite account for yet.
Okay.
But
so
this
is like a work in progress then.
That's a work in progress, but it's also a very difficult problem. We're hoping that this approach will cover the vast majority of cases that actually exist in materials modeling. Right.
Are electrostatics the only long-term thing that you anticipate having an effect on the?
No, there are a few more. So so one is called dispersion, which is actually what the LennardJones potential is designed to capture. Even if you have two completely neutral molecules, they will still, via the weirdness of quantum mechanics, mutually induce dipoles in each other, like induce polarization in each other. And that gives an attraction that goes as like an inverse 6 power or something. So that's another thing that we might have to account for. And there's another set of parameters. It's not quite like partial charges, but there's another set of parameters that we'd have to learn for that. And then the other one is called induction, when one polarized molecule just basically, a bit like a magnet, polarizes another molecule. So that's also very difficult to describe. Any other questions? Yes?
So could you extend this method to magneto hydrodynamics?
In what way?
Well, I don't know.
What about magneto hydrodynamics? Would you mean machine learning, or?
Yeah, I mean, could this be applied to that whole subject, this particular method?
I'm not really familiar with the magneto hydrodynamic equations, so I'm not quite sure how that would work.
Okay. I
mean, this is the idea of fitting a function to data that you have is.
But you're allowing these molecules to move around as though they were in a liquid.
Yeah. Oh, you mean animistic simulations of magneto?
So it might reproduce the properties of a liquid.
Yeah. I think. Yeah, you could do that. I mean, there are various ways of. I mean, it should be not trivial, but easy enough to apply an external electric field, say, to your substance. You might have some weird effects going on with induction and polarization and whatnot, but I think you could do it with magnetic fields. It's just that would be very complicated. Anything else? Well, if not, there is wine and cheese in the MCR, which you don't have to pay for.
Yes, we've got loads and loads of wine and cheese, so please come along and have some. A round of applause for Matt.